Can you see my monitor?
Yes.
Okay. We finished the second exam. I will not discuss the questions of the exam now, but I can tell that the average for most students was 10. The previous exam was 11, and this is the average. The score 11 got by 6 students, 12 by 7, and 13, 14 by 1, 15 by 1, and these by, which are below the average. And the exam, as you see from before, many questions didn't need any solution, just direct answer without just to define quantity or conceptual questions. Okay, our lectures this week about the rotational motion, kinematics, and dynamics. So we'll see, for example, this file, which is the rotational kinematics, contains all the chapter. I will divide it to 2 lectures, so each lecture will be short. Okay, so we will start the rotation of rigid bodies. Now, I'll start by this. We know from before the linear motion. Previously, we know that if there is a person, if he was at x1 at t1, then he move and change his place and or his position to x2 during a time, then we have a change in position delta x and a change in time delta t, and then we can compute, for example, the average velocity or the instantaneous velocity. Also, we can compute or find the average acceleration, which is delta v over delta t, or the instantaneous acceleration. This is the linear motion. We finish it now. And all the quantities, the velocity, the acceleration, the force, the momentum, all of them in linear motion. So the linear means the motion is in straight line. But now we will deal with different thing. We will deal with the rotational motion, okay, or angular motion. For example, if you look, now we will deal with circles always, with angles. For example, before that example, before we deal with the XY plane and the motion in one dimension, for example, on X. Now we will deal with the XY plane, that's right, but we will deal with angles. The motion on circumference of that circle. So for example, at this position, we don't have XY, we have theta. And the time is the same. We have here, for example, theta 1. Here we have theta 2. Here we have theta 3. Okay, so the motion will depend on theta, the angle of rotation. Also, it will depend on the radius. We will see that now. Now the angles on the XY plane, look here at this circle. For example, if we look at the positive x-axis at 0 angle, it is 0 degree at x-axis. We know that it's 0 degree. And it is equal also to 0 radian. We have two systems two systems now to measure the angles, which is the degree or the radian system. And you can see that on your calculator also. So 0 is equal to 0. We will see how to deal with that. At 90 degrees at the positive y-axis, we have pi over 2 radian. At 180 degrees, which is the negative x-axis, it is pi, which is pi in radian. At 270, which is the negative y-axis, it is 3 pi over 2. Again, if we rotate a full rotation, which is 360 degrees, it is 2 pi. Then we can also rotate once, twice, and third, and many times. And we can measure that in degrees or in radians. Pi, you know the value of pi. It is 3.14. It is the same. You can put here 3.14 over 2. For example, 1 radian degree, it is not 1 degree. The 1 degree here, it is very small. But 1 radian, it is equal to almost approximately 75.3 degrees. This is 1 radian. This is 2 radian. This is 3.14 radians, which is pi. Pi equal to 3.14, as you know. So it is 3 radians, 0.14, yes, equal to 180 degrees. So the angular motion in our study now will depend on the radial system. As we said from before, 3.14 is equal to pi, which is 180 in degrees. So 1 radian is equal to 100 degree. We can compute that by take 180 over pi, which is equal to 57. This is a typo. It is 57, not 75. Yes, this is error here. It is 57.3. Okay, I'm sorry about this. I will change it. Okay. Any questions about radian and degree system? Now we have a new type of motion, which is a rotation about a center. This center is the origin, as you see here. We have many examples to rotate about a different point than the center, but we will not deal with them. We just rotate about this center. Now we have some important angles from math. For example, pi over 6, it is 30 degrees. Pi over 6, it is 30 degrees. For example, this angle, it is pi over 3. If we add pi over 6 plus pi over 3, it will be pi over 2, which is 90 degrees. Okay? We have pi over 4, this angle, which is 45 degrees. Okay? For one total rotation, it is 2 pi. Okay? And now be careful. If I ask you about anything in this part of our study, I will tell you I need the grade in radian or in degrees, but almost we will deal with radian. So be careful about your calculator to be in radian system, not in degrees. Okay, I told you from before to be careful. We need the calculators on degrees. I think you have some mistakes in the exams because of this. Some of you. Okay, now what about the rotation, the kind of rotation? When we need to measure any angle, we need to measure it in the direction counterclockwise, like this. it will be positive. If we need to measure to this direction, for example, it will be positive pi over 2, positive pi over 3, or something like that. And the total rotation angle, it is positive 2 pi. But the rotation clockwise direction, like this, it is negative. So going to the right in the rotation, it will be to the negative direction. Okay. The circular circumference, it is easy to compute. We know that from before, from our study from before. We have 2 pi. The 2 pi, it is the total angle that rotate over all the circle. 2 pi multiplied by the radius, r. I put r here, capital R here, small r, there's no difference. Now, this is the radius of the circle. So the radius of the circle multiplied by the angle and radial will give us the circular circumference, okay? What if we don't have total angle, which is 2 pi, if we have part of this angle? Look here, we have theta 1. It is not a total circle like here. Okay, it is just theta 1. And we have the radius r. If we need to measure this section, for the total angle, we use the total, for the total circle, we use the total angle, which is 2 pi, multiplied by the radius, 2 pi. Now we don't have the total angle. We have another angle, which is theta 1. So we just put in the place of 2 pi, which is the total angle, we put our angle multiplied by the radius. Okay? For example, if theta is equal to 1 radian, okay? And the radius is equal to 5 meters. What about the length, this length? So the length will be the angle multiplied by the radius, which is 1 by 5, it is 5 meters. But if we need to measure the total angle of the total circumference for this circle, it will be 2 pi multiplied by r. We need to put 2 pi in the place of theta. For one radius, for the same radius, as you see here, we have the same radius. If we change the angle, then the circular section will increase. So the circular section, this one, depends on r and also on theta. Any question about this? Okay. Before, as we know, if we need to locate the position of any object, we need the coordinate of that object to find the position vector, for example, or just the position. It was x1 or x2 at t1 and t2. Now we will use a different thing. We will not use x and y. The time is the same. Now we will use theta. Theta in the place of x. It's the position angle. Now, if we need to locate any object, we need to know its angle position at any time. Okay? So if we have an object, for example, at this theta or at this theta or at this theta, we need to know the theta and the time. We will deal with the angular motion just like what we did before with the linear motion, but with using the angular position and motion, okay? And our quantities will be in the angular motion, with the angular motion quantities. For example, if our object was at theta 1 and change its position to theta 2 during the time from t1 to to T2. Now we have change in position during a change on time. So we have a rate of change in angular position. So we have delta theta over delta t. Remember from before, we have delta x over delta t, right? We have delta x over delta t. It was x2 minus x1 over t2 over the t1. But now we have change in angular position, which is theta 2 minus theta 1. Now we need to find the rate of change. So the rate of change in theta or in angular position with respect to time, it is the average velocity. No, it is not just the average velocity. It is average angular velocity. Now we have, before we have everything in linear velocity, linear acceleration, linear momentum. Now we have angular, okay? This is the average angular velocity, which is theta 2 minus theta 1 over T2 over T1. The average velocity before, it was V, if you remember that, and you have also. And now we have a different thing. It will be this symbol, which is omega. It is just like the lowercase w, it is omega. So the average angular velocity, we need to say that average angular velocity it is not average velocity or average linear velocity. Omega average is equal to delta theta over delta t. The units of theta is radian, not degrees. The units of time, it is seconds. So the units is radian per second, not meter per second. Okay? Any question about this? Now we know that we change our concept or the way of dealing with the motion from x1 to theta 1, x2 to theta 2. The time is the same. The average velocity now is average angular velocity, which is omega, delta theta over delta t. The unit is radian per second. And as we know from before, the instantaneous velocity, it is the limit when the time goes to 0. Now we have the instantaneous angular velocity. It is omega instantaneous. It is the limit when this change, we don't have vast change in theta and time. We have small changes. In these small changes, delta will convert to d, which is a small change. Okay. Now we have this example. It is very simple because now we know how to deal with the velocity, with the acceleration. We didn't talk about the acceleration. It will be the same, just like the same as the linear acceleration. It is now more simple to deal with the velocity, the acceleration, because when we know what these concepts means, what these quantities mean, but now we will deal with them in angular motion. Okay, if we have theta 0, theta n, theta 2, we have 3 positions and we have 3 times. The object was, maybe it's a car rotate around the circle, or an object just rotate, or a planet rotate around the sun, or something like that. We have theta 0 at t0 equal to 0. It is here at the positive x-axis. There's no need to draw xy plane now. We need just to know the theta and the radius. This is our coordinate system now. We have theta 1. It is pi over 6, which is 30 degrees. And the time is 1 second. This is theta 1, pi over 3, over 6. This is my position, the first position. The second position at theta 2, which is pi over 3, which is 60 degrees, at t equal 3 seconds. Theta 3 here, it is equal to 2 radian, which is 114. If you remember, 1 radian is equal to 57.3. So 2 radian equal to 114.6 degrees. And I will tell you how to convert between radian and degrees. It is just convert between units. At time equal to 8 seconds. So we have the position and the time. We can find the velocity between, or the average velocity between any 2 points. Now find W1. I'm sorry, not W, omega. Before we dealt with the W, with the work and with the weight. Now this is omega. It's equal to theta 1 minus 0 over delta t. Okay. Theta 1, it's pi over 6, which is equal to 0.524 minus 0. This one minus 0 over 1, which is 1 minus 0. It will be 0.524 radian per second. So the average velocity of this object when it moves from this point to this point is 0.524 radian per second. Okay. What if we need to find the average velocity from point 1 to point 2? It is theta 2 minus theta 1 over t2 minus t1. It's just the same as before we did before. It's delta x over delta t. Now we have delta theta over delta t. Delta theta, pi over 6, pi over 3, which is theta 2. It is 1.05 minus theta 1 over delta t. It will be now 0.26 radian per second. So the average velocity here is different than the average velocity in this period. For example, what about omega? I name it here 4, which is from this position to this position. It will be equal to delta theta, which is 2 minus pi over 3, which is 1.105 over delta t, which is 8 minus 3. It will be 0.19 radian per second. So I can compute the average velocity between any 2 points. It is simple and not complicated. Okay, we did that from before for the linear motion. Any question about this? Now we can compute also the acceleration, which is the angular acceleration. If we have 2 angular velocities, as you see here, omega 1, omega 2, omega 4. It should be omega 3, I don't know why. Okay. The average angular acceleration, remember from before, the linear acceleration, it was delta v over delta t. We saw that. Now we have the average angular acceleration. It is delta angular velocities over delta t. Omega 2 minus omega 1 over t2 minus t1. The linear acceleration was a, its sample, okay? Remember that, a. Now we have this sample, which is alpha. Okay, we use alpha for angular acceleration. The average angular acceleration. Also, we have the instantaneous angular acceleration. It is the limit when the time and the change in velocity goes to small values. It will be d over d. It is not delta. Okay. Now, before, we know in linear motion, we have the speed and the average speed and the acceleration. If we have, for example, a car, or let us go back to this example. If we have this velocity for this person, if the velocity from here to here is, for example, 5 meters per second for this person, assume maybe it's a car, maybe it's a person or something like that. The parts of this object, his hands, his head, are moving with the same velocity because all the objects move with this velocity. But rotational motion, it is different. The velocity for the far objects is different than the velocity. I'm not talking about the angular velocity now. It's different than the velocity of the closest object to the center. We are here now. Here, I'm talking about the linear speed. If we have a stick, and this stick has a length R2, its part at R1, and when we rotate it, the speed, I'm talking about the linear speed, or the, not the angular, the speed at R2 here is faster than the speed at R1. You know that. If you are rotating an object with a thread or a string, and your string is longer than the speed of this object, at the end of this string, it will be faster than the speed at this point. Okay? That is for the same theta and the same time. If we need to compute the speed, the linear speed, or in this case, it will be the tangential speed at this circumference, part of the circle, it will be a tangential speed. The tangential speed in this case, it is equal to this length divided over the time. This length S2, this length is S1. If we need to find what is the ratio between them, we can see that from here. S2, as we see from before, we can compute it by the radius multiplied by the angle, which is theta 2, which is equal to theta 1 for S1. So S2 and S1 have the same angle, but they have different radii, okay? So S1 is shorter, as you see, shorter than S2. So if you need to compute the tangential speed, if an object moving on this longer distance, it will be fastest than this one. We have some examples about this. Now, if you remember from before, we have the velocity is a vector, the acceleration is a vector. Is there any vectors in rotational motion? Yes, we have. There is a direction of the change in theta and omega and alpha. For example, for the rotating of the arms of the fan of this helicopter, the rotation is in this direction, as you see, which is the horizontal level. But the direction of this rotation, it is not in X, it is not in Y. The rotation is about an axis, and this axis is the Z axis. Okay? If the rotation about some about a certain axis, then we can say that the rotation has a direction, and the direction of that rotation is that axis. So the rotation of omega, because omega is a velocity, it's a speed. So this speed is about z direction. If we have the back fan, for example, this one, its rotation about maybe x-axis. Not, you know that the direction of this fan, of rotation of this fan, different than the rotation of this fan. This fan is rotating about the z-axis, but this fan rotating about a different axis, which is x or y, which is perpendicular to z-axis. For example, we have x, y, z plane, space. If we have this rotation, x and z are rotating now like this. The rotation is about y. Then the rotation direction is y hat. If we have the rotation about z, then the xy plane are rotating about the z-axis. So we have rotational direction. And we have also acceleration. From before, you know that the change in velocity or the change in position has a direction because we have position vector. And the change in position direction is the same as the velocity direction. Here we have also for this bicycle, we have a rotational angle, a rotational direction, which is about the x-axis, for example. So when we talk about the rotation, we need to know also we have a directions, and these directions is the axis of rotation. Any question about this? Now we'll talk about the rotational kinematics, which is the rotation with constant angular acceleration. This will be also simple, just as we did from before. Remember from before, we have the linear motion and we have the equations of motion, which is the first level when we need to discuss any moving system. Let us look at this system and the example. We have the equations of motions V2 equal to V1 plus AT, V2 square is equal to V1 plus 2A X, and we have the X equal to these things. We know these equations. And for example, we have this example. If we have, and you see like this one in the exam, we have X1, X2, we have the velocity initially, which is 5 meters per second. We don't know how much the velocity finally. We have the acceleration. During 10 seconds, I need to you to find the velocity finally. You will use the first equation. It is the most simple one. So V2 equal to V1 plus AT. You need to put the numerical values. You need to understand the problem. It is a moving object in a linear way. And then you can find the final velocity. Also, you can find the change in position, which is delta x, by using this value, this equation, or this one. We know that from before. In rotational motion, we have the same thing. As I told you from before, we have x, we have theta in rotational motion. We have V1, we have omega 1. We have V2, then we have omega 2, it's the final velocity. We have the acceleration A, we have the angular acceleration alpha. Now, these equations, we have the same as them, but in rotational or angular motion. We have V2, we have omega 2 is equal to omega 1 plus alpha t. It is the same, but the velocity is omega, the acceleration is alpha. We have omega 2. We will see later we have a relation between V and omega. We have omega 2 squared is equal to omega 1 squared plus 2 alpha theta. Theta is x, alpha is the acceleration, the same in linear motion. The 2 is 2. The time is the same. And also we have theta is equal to theta naught plus omega naught t plus half alpha t squared. They are the same as this one, but with theta, omega, and alpha. This is an example just like this one, but the motion, it is not linear here. It is angular. For example, if we have the initial angular velocity, it is 2 radians per second here when we was here. During 5 seconds, our object moved, not delta x, it moved delta theta. With acceleration, half radian per second. Half radian per second. This is the acceleration, which is the angular acceleration. I ask you to find omega 2 and find delta theta. Here, I ask you to find V2 and delta x. I didn't find delta x. No, I find it here. If you complete solving the example, delta x, x2 is equal to x1 plus v1 v0t plus half at squared. I find here x2 is 205 meters. So we find all the unknowns. Here, we need to find omega 2. Just as we apply here, we need to apply here, which is omega 1, it is 2. Alpha, it is half. The time during 5 seconds. If I gave you the same numerical values here, you need to put them. It is the same. But I here gave you different values. So omega 2 is 4.5 radian per second. What about with acceleration, constant acceleration 0.5 radian per square second. The acceleration is radian per square second, but the acceleration, linear acceleration meter per square second. Okay, what about the change in position? We need to use the third equation. Just theta. Now here we find delta theta. It's just I move theta 0 to this position. It will be theta minus theta 0. It will be equal to theta omega 0 multiplied by t, which is this term, plus half alpha t squared. Just put the values. 2 multiplied by 5 plus 0, half multiplied by half, multiplied by the time square, which is 5 squared. It will be equal 16.25 radians. This is the change in position. The change in position. Okay, the change in theta. As you see here, it is the same as the linear motion, but with angular quantities, theta, omega, and alpha. Any question about this? I don't know, there's no chats, okay. Okay, I think I will discuss this. Okay. Finally, today, I think I will discuss this part, which is okay. Which is what is the relation between linear and angular kinematics? Now we will see what is the relation between omega and V. What is the relation between A and alpha? What is the relation between theta and X? I told you there is a relation between them, and we will see that now. So we need to find the relation or the connection between the linear and the rotational quantities. Now, from the circle, we know that the circumference for the circle is a linear quantity. It is a length, okay? It is not angular quantity. This is, which is S, it's a length, okay? It's a distance, not a displacement. It is not a vector. This length has a relation with the angle. And you know that S here is equal, which is the total circumference for the circle, is equal to 2 pi r. The total circumference has a relation with the total angle. But if we have just a section, like what we see here, I'm sorry, the part S here, this part S has a relation with its angle. This relation between S and the angle between S2 and theta 2 is the connection between these things, these quantities, which is the length and the angular position, is the radius. Just it is multiplied by radius. If we need to change from angular position to the linear position, we need just to multiply it by the radius. And we will see that here. The time is the same in linear motion and angular motion. For the total rotation, we have a total time. This total time named the period, okay? So if we need to find a velocity, if this speed, we are not in linear motion now. We are, I mean, it is not a vector quantity. It is just speed. Now we have a speed about this circumference, okay? This circumference length is S. If we need to find the velocity or the speed for this distance, it is the length divided over the time. The length is S. The time is T. This is the velocity. Oh, I'm sorry, the speed. This is the speed. If we need to find its direction at a point, it's a tangential, okay, to that point. What about the rotational motion? The rotational motion is S is equal to 2 pi r. R is the radius. 2 pi is the angular position change, which is if we were here, then we change our position. To be here, we change our position by 2 pi. Yes, that's right. It seems that we rotate and we get back to the same point, but no, we change our position by 2 pi, which is 360 degrees. During a time, T capital, which is the period. So the speed or the angular speed is 2 pi over T. But we have the radius R will connect our angular motion with the linear motion. So the connection between the linear motion and the angular motion is the radius, as you see here. The change in angular position is the angular velocity. Look here, the speed is equal to S over T, which is equal to 2 pi R, which is S over T. Now in physics, I told you from before, we can change the position of any quantity. So we can take R outside from this. It will be 2 pi over T. 2 pi is angular position, change in angular position over the time. This is angular velocity. Angular velocity. It is multiplied by R. So the speed, it is the radius multiplied by the angular velocity. So there is a connection between the speed, which is the tangential speed. This is T, means tangential speed. There is a relation between the tangential speed and the angular speed, which is the radius. Okay. We know from before, we have the radial acceleration or centripetal acceleration, which is V squared over R. Now we will talk about the acceleration. We have it, V squared over R. V, it is the same like this V, which is the tangential velocity. V squared, it is R squared omega squared, like this. R is the same R. So we have the centripetal acceleration is R squared omega squared over R. It will be R omega squared. Now, in this case, if we have any change in, now this is the centripetal acceleration, which is the omega squared multiplied by R. What if we have, from, look here to this example, if we have change in velocity, linear velocity, during the time, then we have acceleration if we have a change in velocity. And we know that also if we have a change in angular velocity, if we have change in angular velocity, then we have a change in, we have acceleration, which is, we have alpha. By the same thing, if we have tangential acceleration, because we have a change in the velocity, in the speed with the respect to time, then we have a tangential acceleration. This tangential acceleration is also equal to the radius multiplied by the angular acceleration. Now we have the tangential velocity is equal to R multiplied by omega. The tangential acceleration is equal to R multiplied by alpha. So the relation between the linear quantity and the radial quantity is R multiplied by the radial quantity. Okay. Now, for any rotational motion, we have two accelerations. One of them is to the center, which is the centripetal acceleration, which is V squared over R. AC V squared over R, or R omega squared. Okay, this is the radial one. We have tangential acceleration, which is R alpha. This one, it is tangential direction. So we have in any rotational motion, sometimes the tangential acceleration is equal to 0. If the rotational velocity is constant, then the tangential acceleration is 0. But if we have two accelerations, they are vectors. Then we have a resultant acceleration. We can know it by just finding, we have, because they are, the radial one is to the radius, to the center, direct to the center. The other one is tangential. The angle between them is 90 degrees between AC and AT. Because of that, we can use the Pythagorean theorem to find the resultant one. So the total acceleration will be AC squared plus AT squared. If we need to find the phi here, which is the direction of that acceleration, we can use also the tan inverse, which is AC over AT. Okay, the tangential acceleration is equal to, this is the tangential acceleration, R alpha, square it. AC, it is R omega square it will be R square omega to the 4. This is the total acceleration. Any question about this? Okay. Now we have this example, which is the final page for today. Okay, if we have a rotating car with around the circle and the radius of that circle is 25 meters, the velocity tangentially is 20 kilometers per hour. It's a car, and the its velocity or its speed. When we talk about the tangential, we can say velocity because we know the direction. And we have acceleration is tangentially is 2 meters per second, square second. So we have speed or velocity, and we have acceleration tangentially for this car. We need to find everything. We need to find the angular velocity. We need to find the angular acceleration. We have to find the angular, no, the radial acceleration, which is A centripetal or A radial. We need to find the total acceleration, which is this one. And we need to find the direction of that acceleration. Okay, it is simple. What about our velocity is in kilometer per hour. The acceleration, it is ready, meter per second, but we need to convert this to meter per second. Again, 20 kilometers per hour, we need to multiply it by, we need to convert from kilometer to meter, from hour to seconds. We need to, this is the coefficient of conversion from kilometer to meter. This is from hour to second. Hour will cancel with hour, kilometer will cancel with meter. Each 1,000 meter is equal to 1 kilometer. Each 1 hour equal to 3,600 seconds. Then our velocity now, tangential, is 5.6 meter per second. Okay. Now, from the relations, we have that V tangential is equal to the radial velocity, radian velocity multiplied by the radius. Vt is given, radius is given. We need to find omega. This is the first thing. Okay, omega is 5.6 over 25, which is the radius. This radius, 25 meters. So omega, which is the angular velocity, is 0.22 radian per second. Okay, what about the radian acceleration or angular acceleration, alpha? It is AT over R. AT is given 2. The radius, 25. 2 over 25, it will be 0.08 radian per square second. We have a square here. I'm sorry for this. Okay. What about the centripetal acceleration or radian acceleration? It is V square over R. or the same thing, r omega square, because we found that from before here. AC is V square over R, but V is equal to R omega. Then the centripetal acceleration is R omega squared. We can find it by the two ways. V square over R. V is, we found it. This is V, 5.6. 5.6 square over 25, it will be 1.2 meters per square second. This is the radian or centripetal acceleration, which is the acceleration toward the center. If we need to find it by R omega square, R is 25, omega is 0.22, we just found it. Squared, it will be 1.2 meter per square second. It is the same. Okay, what is the total acceleration? Now I need to find this total acceleration. I have tangential acceleration. We have also radial acceleration. We have two vectors. They are perpendicular to each other. Then we can use the Pythagorean theorem. The total acceleration is equal to the first one square plus the second one square under the square root. The square one is the tangential acceleration is 2 squared. The centripetal acceleration is 1.2. We just found it. 1.2 squared. So the resultant acceleration is 2.3 meters per square second. So this value, 2.3. What about the phi? Phi, we have this angle. The opposite is AC. The adjacent is AT. Using tan inverse to AC over AT, phi will be 30.96 degrees. Okay, you can convert it to radian. We don't need to do that. I will tell you about that later. But that's it. In this case, we found everything. We found the velocity, the acceleration. And then we, in the next meeting, inshallah, we will deal with the rolling motion. Any question about today's quantities? Again, the main thing, we can use these equations to differentiate between our previous knowledge, which is velocity, linear acceleration, change in linear position, which is x. Just we could need to convert. I told you about this point. We need to convert all of our knowledge, convert it to angular study. Just omega, theta, and alpha. Any question about this? I didn't put yet homework about this. I will put it for tomorrow's lecture. I hope I can come tomorrow to the classroom to discuss this on the blackboard. If you have any questions, if you have to meet with me after the class today, just tell me. I will be on Zoom. The medications will have a side effects to make me more tired, but it's okay. Okay, any question for today? I'll talk about the exam in the end of this week. I'll stop sharing at this point. And if you don't have any questions, thank you for today.